When you hear the Big Bang Theory, you may think of the popular sitcom. But today, we're talking about the real Big Bang, the prevailing cosmological model for how our universe began. The theory says that the universe started out as a hot, dense ball of matter and radiation known as a singularity. Then, approximately 13.8 billion years ago, this singularity exploded and expanded outward in all directions, and it still is to this day. And that expansion continues to speed up. But why did the Big Bang happen? No one knows. To answer that question would require physics beyond Einstein's general relativity, which describes how gravity works on large scales. However, general relativity tells us what happened right after the Big Bang. Let's dive in. For the first few minutes after the Big Bang, the universe was filled with a thick soup of elementary particles like quarks and electrons. At first, these particles were moving so fast they couldn't form anything more complex. They were in a state of thermal equilibrium, meaning that if you looked at any two particles, they would have roughly the same temperature. But as the universe expanded, it cooled, allowing those particles to combine and form larger things like protons and neutrons. This process is called hadronization, and it occurred about 200 microseconds after the Big Bang when the temperature had dropped to about 2 trillion degrees. At around the same time, protons and neutrons combined to form atomic nuclei, kicking off an era known as Big Bang nucleosynthesis. During this time, most of the protons and neutrons fused together to make mostly hydrogen and some helium. You won't find much of anything heavier than helium in our observable universe because there wasn't enough time for more nuclear fusion to occur. Once the universe had cooled enough for atoms to form, a new era called the Cosmic Dark Ages began. These were dark times because the universe was mostly transparent, meaning light could pass through it easily. The only thing that existed was a sea of particles and the photons that bounced off them. Photons are the particles of light. In order to get out of the Dark Ages, the universe needed something that would scatter light like a wall, creating space where photons could bounce around and give rise to the microwave background radiation we see today. That's where the first stars come in. As the universe continued to cool, hydrogen and helium collapsed under their own gravity to form the first stars and galaxies. Light finally had something to bounce off of, and this ended the Dark Ages and ushered in the era of reionization. During reionization, the universe became opaque again due to the creation of plasma clouds made of free electrons and ions. This allowed light to travel only a few dozen of the 19 kilometers before being absorbed by a free electron. But just as in the Dark Ages, as the universe continued to expand and cool, those electrons eventually combined with ions to form neutral atoms. With fewer free electrons floating around, light could finally travel long distances without getting absorbed. This transition from opaque to transparent is called the epoch of reionization, but we don't know exactly when it ended. We can only observe what's in our observable universe, and since light takes time to travel, we can only see back to a certain point. The edge of our observable universe is the surface of the cosmic microwave background, or CMB, and it represents the universe as it was 400,000 years after the Big Bang. Beyond that, we cannot see. So, while we can study the CMB to learn about the early universe, we can't see the epoch of reionization, which means we don't know for sure when the universe became transparent. But scientists have managed to indirectly measure the CMB to estimate when this would have occurred. One of the ways they do this is by looking at the polarization patterns of the CMB, which give us information about how the light got to us. In 2014, researchers using the BICEP 2 telescope in Antarctica claimed they detected a pattern of polarization in the CMB that suggested the presence of gravitational waves. If true, this discovery would have been huge. Gravitational waves are ripples in space-time predicted by Einstein's general relativity. They were first detected here on Earth in 2015, but this detection would have been the first evidence of gravitational waves from the Big Bang. Unfortunately, subsequent research found that this signal was likely caused by dust in our galaxy, not gravitational waves. but this highlights one of the ways scientists learn about the early universe, studying the patterns in the CMB. Another way is by looking at the cosmic microwave background directly. The CMB is actually a few minutes old. It took 13.8 billion years for the light to reach us, and when we look at it, we see an almost perfectly uniform sea of microwaves coming from all directions. The temperature of this radiation is about 2.7 Kelvin or 2.7 degrees Celsius. But no, that's not absolute zero, the coldest possible temperature. Absolute zero is the absence of heat, the point at which all molecular motion stops. Because nothing can be colder than the absence of molecular motion, it's impossible to reach absolute zero. If you thought maybe I'm just really bad at physics, don't worry. Even the best physicists can't reach absolute zero either. There's always some motion, even if it's just a single photon bouncing around. But anyway, that's not what I was talking about. I meant the cosmic microwave background is 2.7 Kelvin above absolute zero. The reason the CMB is so uniform tells us a lot about the early universe. This uniformity implies that the conditions were very similar throughout the entire universe at the time the CMB was emitted. Otherwise, different regions would have appeared hotter or colder. But the fact that they don't suggests that the early universe was in a state of thermal equilibrium, meaning everything was evenly distributed and moving around like a pot of boiling water, and yet we do see tiny variations in the CMB. And these variations tell us another crucial piece of information: how matter began clumping together to form the first stars and galaxies. Those tiny variations from perfect uniformity are adiabatic sound waves created during the Big Bang, the quantum fluctuations of space-time stretched by exponential inflation and then frozen in place when inflation ended. These primordial fluctuations gave rise to the seeds of the large-scale structure of the universe. Since the average matter density is about 5% higher where the CMB is slightly hotter, those regions would have had slightly higher densities of matter even before gravity had a chance to kick in. So these density variations acted as seeds for gravity to work on. Gravity caused overdense regions to collapse into stars and galaxies, while low-density regions had fewer particles to pull together. Over billions of years, those differences in density have grown, leading to the universe we see now. All this is to say that we have a lot of information about the early universe, even though we can only observe the remnants of it. It's like trying to reconstruct a story from a few minutes after the beginning by reading the last page. Sure, there are some details we might be missing, but we can still get the gist of what happened. And that's how we know that despite the vastness of space and the limits of our own planet, we are forever linked to the events that occurred at the beginning of our universe. So, that's a wrap. It's been a blast diving into these mind-bending ideas with you. Remember, the mysteries of the universe are endless, and there's always something new to explore. Until next time, take care and keep that curiosity alive.